A bead of mass m without friction on the wall of a vertical hoop of radius r as shown in figure. The bead moves under the combined action of gravity and a massless spring attached to the bottom of the hoop. The equilibrium length of the spring is r if the bead is released from the top of the hoop with zero initial velocity. Velocity of the bead when the length of the spring becomes r. Okay. Now the bead is starting from here and it is moving in a circular path. They are saying that there is no friction here. So as friction is absent, we'll apply a conservation of energy. Okay. Now they are saying that the bead moves under the combined action of gravity and massless spring. So there will be gravity here and there will be a spring force. Now there will be normal force also, but as the displacement is along the vertical movement, there is it was a perpendicular, so no matter of normal force here. And they are saying that equilibrium length of the spring is r. What is meant by equilibrium length? That is natural length of the spring, but it was expanded to 2r, but actually that's the natural length was r if the bead is released from the top of the hoop with zero initial velocity. There is an initial velocity 0. Okay. Now they are asking at a velocity when the spring length was r. So as bead moves, the spring also becomes like this. Okay. Bead is moving like this. They are asking at some point the length of the spring is r. This was the length of the spring. Okay, now let's consider this as center. Now this radius was r and this was the radius r. We know that as the three sides are equal in equilateral triangle, we'll have a angle as 60 degrees. So if we draw perpendicular like this, it is 90. Now what is this length? This length was total 2r. 2r minus, now this was r cos 60, right? This was r cos 60, which is r by 2. So 3r by 2. So initial height minus final height was 3r by 2. So mg into 3r by 2. So initially we'll have some we don't have any velocity, right? So 0 kinetic energy plus we'll have some spring force, that is half k x square. That x is nothing but r, which is spring's natural length, is equal to, finally we have some velocity half m v square. Now by solving this, v square is equal to mg into 3r by 2 plus k by 2 r square into 2 by m. So v is equal to root 3 gr plus k r square by m. This was the final answer.